Welcome to Sleepy Science Odyssey. Tonight, Earth, the planet beneath your feet, the only world in the universe known to harbor life, spinning through space at thousands of kilometers per hour while you stand still on its surface. We'll move slowly through deep time and vast processes, from the planet's violent formation 4.5 billion years ago to the intricate systems that make it habitable today. From the molten core, generating a protective magnetic field to the thin atmosphere shielding the surface from radiation, from tectonic plates drifting across eons to the water cycle connecting ocean, sky, and land. If you're new here, this channel is for people who need something to think about before they can stop thinking. Real planetary science, no exaggeration, just quiet facts in the dark. Let's begin. Earth formed approximately 4.54 billion years ago from the solar nebula. The solar system began as a vast cloud of gas and dust, the remnants of earlier stars that had lived and died, enriching space with heavy elements forged in their cores and scattered in supernova explosions. About 4.6 billion years ago, something disturbed this cloud, perhaps a nearby supernova's shockwave, perhaps gravitational interactions with passing stars, triggering its collapse. As the cloud collapsed under its own gravity, it began to spin, flattening into a rotating disk. Most of the mass fell toward the center, where temperatures and pressures eventually became high enough to ignite nuclear fusion, and the sun was born. But not all the material fell into the sun. The remaining disk of gas and dust began to clump together through countless collisions, particles sticking to one another, gradually building larger and larger bodies. In the region where Earth would form, approximately 150 million kilometers from the newborn sun, temperatures were cool enough for rocky materials and metals to condense, but too warm for volatile compounds like water and methane to freeze. Dust grains collided and stuck together through electrostatic forces and gentle collisions, building pebbles. Pebbles merged into rocks, rocks into boulders, boulders into kilometer-sized planetesimals. These planetesimals had enough gravity to attract additional material, accelerating their growth. Over millions of years, the larger planetesimals grew through accretion, sweeping up smaller bodies in their orbital paths. The process was violent. Collisions generated tremendous heat, melting incoming material and keeping the growing Earth partially molten. Eventually, a handful of planetary embryos, perhaps a few dozen Mars-sized bodies, dominated the inner solar system. These embryos gravitationally influenced one another, their orbits gradually becoming unstable. Collisions between planetary embryos were catastrophic, melting the surfaces completely and sending debris into space. Earth itself experienced numerous giant impacts during this period, each adding mass and heat. The young Earth was a hellish world. Its surface was an ocean of molten rock, magma constantly churned by tidal forces and heated from within by radioactive decay and continued impacts. The atmosphere, if it existed at all, was likely vaporized rock and metals, nothing like the nitrogen-oxygen mixture we breathe today. The entire formation process from dust grains to a nearly complete planet took perhaps 100 million years, an eye blink in geological terms, but an almost incomprehensibly violent period when the Earth was built from countless collisions, each adding mass, heat, and angular momentum. By about 4.5 billion years ago, Earth had reached approximately its current mass, though its surface remained molten and its composition would continue evolving as heavier elements sank toward the core and lighter materials rose toward the surface, a process called differentiation. This differentiation was driven by gravity and density differences. Iron and nickel, being dense, sank toward the center, eventually forming Earth's metallic core. Lighter silicate minerals floated upward, eventually forming the mantle and crust. This process released enormous gravitational potential energy, further heating the planet. The young Earth was essentially a ball of molten and semi-molten rock, slowly organizing itself by density, with the heaviest materials sinking and the lightest rising. This separation into layers, core, mantle, crust, established the basic structure that persists today, though the details have evolved over billions of years through ongoing geological processes. The heat from formation was so intense that Earth may have remained largely molten for tens of millions of years. Eventually, heat radiated into space faster than it was generated internally, allowing the surface to cool and solidify, forming the first solid crust. This early crust was probably basaltic, similar to oceanic crust today, and unstable. It likely repeatedly melted and resolidified as impacts continued, and as internal heat tried to escape. The transition from a molten surface to a stable solid crust was gradual and probably occurred in fits and starts over tens of millions of years. The Moon formed from debris after a Mars-sized object collided with Earth. Shortly after Earth reached approximately its current size, perhaps 4.51 billion years ago, it experienced the most catastrophic impact in its history. A planetary embryo about the size of Mars, sometimes called Theia, struck Earth at an oblique angle. The impact was almost beyond comprehension. It released energy equivalent to billions of nuclear weapons, vaporizing much of both bodies. The cores of Earth and Theia merged, with Theia's iron sinking into Earth's interior. But enormous amounts of material from both mantles were ejected into orbit around Earth, forming a disk of vaporized and molten rock circling the planet. This disk of debris gradually coalesced into the Moon over perhaps thousands of years, particles colliding and sticking together, gravity pulling the mass into a spherical shape. The Moon formed close to Earth, perhaps only 20,030,000 kilometers away compared to today's 384,400 kilometers. At this distance, the Moon would have appeared enormous in Earth's sky, perhaps 15-20 times larger than it appears today, dominating the sky as a molten, glowing sphere. Tidal forces between Earth and Moon were immense. These tidal forces slowed Earth's rotation. The young Earth may have rotated once every 5-6 hours immediately after the impact, but tidal friction gradually slowed it. Simultaneously, the tidal interaction transferred angular momentum from Earth's rotation to the Moon's orbit, causing the Moon to gradually spiral outward, a process that continues today at about 3.8 centimeters per year. The giant impact hypothesis, now the leading explanation for the Moon's origin, elegantly explains several puzzling features of the Earth-Moon system. The Moon's composition is remarkably similar to Earth's mantle, but differs from Earth's core. It formed primarily from mantle material ejected in the impact. The Moon is large relative to Earth compared to other planet-Moon pairs in the solar system. It formed from the debris of a massive collision rather than from accretion or capture. The Earth-Moon system has unusually high angular momentum. The collision added rotational energy, and oxygen isotope ratios in lunar samples are nearly identical to Earth's, suggesting they formed from the same material or that the material was thoroughly mixed in the impact. The Moon's formation had profound consequences for Earth's subsequent evolution. The impact added enormous heat, completely melting Earth's surface and perhaps much of its mantle. This reset Earth's geological clock, erasing any earlier crustal features. The impact may have stripped away much of Earth's early atmosphere, requiring volatiles to be redelivered by later impacts. And the Moon itself has stabilized Earth's axial tilt over billions of years, preventing the chaotic climate variations that might occur if Earth's obliquity wandered freely, potentially making Earth more hospitable to life. Without the Moon, Earth's tilt could vary from 0 to 85 degrees over millions of years, creating extreme seasonal variations. With the Moon, the tilt varies only between about 22 and 24.5 degrees over 41,000-year cycles, maintaining relatively stable climate patterns that have allowed life to flourish. The Moon's stabilizing influence on Earth's tilt operates through gravitational torques. Earth's equatorial bulge, caused by rotation, provides a handle that the Moon can pull on gravitationally. This interaction would normally cause Earth's rotation axis to precess wildly, but the Moon's substantial mass and proximity creates strong enough torques to damp out large variations, keeping the tilt relatively stable. Mars, lacking a large moon, experiences chaotic tilt variations that likely cause dramatic climate swings, potentially making the surface less hospitable for sustained life. The young Moon was also tidally heated by proximity to Earth, possibly maintaining a magma ocean on its Earth-facing side for millions of years. As it cooled and solidified, the Moon became tidally locked to Earth, always presenting the same face toward us. This occurred because tidal friction slowed the Moon's rotation until its rotational period matched its orbital period. The far side of the Moon, never visible from Earth, was only revealed when spacecraft photographed it in 1959, showing a surface with far fewer dark maria than the near side, possibly because the crust is thicker on the far side, making it harder for magma to reach the surface and form maria. Earth is the largest of the terrestrial planets in the solar system. Earth has a diameter of approximately 12,742 kilometers at the equator, slightly larger than Venus, 12,104 km, significantly larger than Mars, 6,779 km, and far larger than Mercury, 4,880 km. Earth's mass is about 5.972 times 10^24 kilograms, representing more mass than all other terrestrial planets combined. This size places Earth at an interesting threshold, large enough to retain a substantial atmosphere through gravity, to maintain internal heat driving geological activity, and to generate a magnetic field through a convecting liquid iron core, but not so large that it captured and retained massive amounts of hydrogen and helium from the solar nebula, which would have made it a gas giant rather than a rocky planet. Earth's size and mass give it a surface gravity of 9.8 meters per second squared, strong enough to hold an atmosphere, but not so strong that it crushes surface features or prevents mountains from rising. The escape velocity from Earth's surface is about 11.2 kilometers per second, fast enough that most atmospheric molecules, which move at average speeds well below this, are retained over billions of years, though the lightest elements like hydrogen and helium gradually leak away into space. Atmospheric retention depends on comparing molecular speeds to escape velocity. At a given temperature, lighter molecules move faster than heavier ones. Hydrogen molecules at Earth's surface temperatures move at average speeds around 2 kilometers per second, much less than escape velocity, so most hydrogen is retained on human timescales. But over geological time, occasional hydrogen molecules in the high-speed tail of the velocity distribution reach escape velocity and are lost. Helium, the next lightest element, is also gradually lost. Heavier molecules like nitrogen, Oxygen and carbon dioxide have much lower speeds and are effectively permanent on geological timescales. Earth is not a perfect sphere, but an oblate spheroid, bulging slightly at the equator due to its rotation. The equatorial diameter is about 43 kilometers larger than the polar diameter. This equatorial bulge develops because rotation creates centrifugal force that pushes material outward at the equator where rotational velocity is highest. The effect is small. Earth is round to within 0.3%, but measurable and important for satellite orbits and understanding Earth's gravitational field. A satellite in low Earth orbit experiences slight variations in gravitational pull as it passes over the equator versus the poles, requiring orbital calculations to account for Earth's true shape rather than assuming a perfect sphere. Earth's shape is actually more complex than a simple oblate spheroid. Variations in internal density, mountain ranges, ocean trenches, and other features create subtle variations in gravitational attraction. The idealized shape accounting for these gravitational variations is called the geoid, an irregular surface representing constant gravitational potential. If the oceans covered the entire Earth and were perfectly still, they would conform to the geoid surface. The geoid has bumps and depressions corresponding to density anomalies deep in the mantle and crust. Satellite measurements of Earth's gravitational field from missions like GRACE, Gravity Recovery and Climate Experiment, map the geoid with remarkable precision, revealing information about subsurface density distributions that help geologists understand mantle convection, plate tectonics, and other processes. Earth's rotation has slowed over geological time due to tidal friction with the Moon. Currently, Earth rotates once every 23 hours, 56 minutes, and 4 seconds relative to distant stars, the sidereal day. A solar day from noon to noon is slightly longer, 24 hours, because Earth moves along its orbit, requiring slightly more than one complete rotation for the Sun to return to the same position in the sky. Early in Earth's history, days were much shorter. Approximately 4 billion years ago, a day may have been only 6 hours long. About 620 million years ago, based on growth patterns in ancient corals and rhythmites, sedimentary rocks recording tidal cycles, a day was approximately 21.9 hours, and a year contained about 400 days. The year hasn't changed. Earth's orbital period around the Sun is determined by the Sun's mass and orbital distance, neither of which has changed significantly. But the number of rotations per orbit has decreased as each rotation takes longer. The gradual lengthening of the day continues. Currently, each day is getting longer by about 1.7 milliseconds per century due to ongoing tidal friction. In 200 million years, if the current rate continues, a day will be about 25 hours long. The mechanism is the tidal bulge raised in Earth's oceans by the Moon's gravity. The bulge tries to align with the Moon, but Earth's rotation carries it forward slightly. The Moon pulls backward on this displaced bulge, exerting a torque that slows Earth's rotation. Simultaneously, the gravitational pull of the displaced bulge on the Moon pulls it forward in its orbit, speeding it up, which causes it to move to a higher orbit. Energy and angular momentum are conserved. Rotational energy is converted to tidal heating and transferred to orbital energy. Earth's interior is layered into distinct zones with different compositions and properties. Beneath the thin, solid crust lies a complex interior structure revealed through seismic waves generated by earthquakes. When earthquakes occur, they produce several types of waves that travel through Earth's interior. P waves, primary waves, are compressional waves that can travel through both solid and liquid. S waves, secondary waves, are sheer waves that can only travel through solids. By measuring how these waves travel, their speeds, and where they appear or disappear at seismic stations around the world, geophysicists have mapped Earth's interior with remarkable precision without ever drilling more than a few kilometers deep. The deepest hole ever drilled, the Kola superdeep borehole in Russia, reached only 12.3 kilometers, barely scratching the crust. Yet seismic waves have revealed the structure down to Earth's center at 6,371 kilometers depth. The outermost layer is the crust, ranging from about 5-10 kilometers thick beneath oceans to 30-70 kilometers thick beneath continents. Oceanic crust is primarily basalt, a dark, dense volcanic rock rich in iron and magnesium. Continental crust is primarily granite and related rocks, lighter in color and density than oceanic crust, enriched in silicon and aluminum. The boundary between crust and mantle is called the Mohorovičić discontinuity, or MOHO, named after Croatian seismologist Andrija Mohorovičić, who discovered it in 1909 by noticing that seismic waves abruptly increased in velocity at a depth corresponding to the crust-mantle boundary. The change in velocity reflects a change in composition and density. The mantle is denser than the crust, containing different minerals with different seismic properties. Below the crust lies the mantle, extending to a depth of about 2,900 kilometers, comprising about 84% of Earth's volume. The mantle is primarily solid rock, mostly composed of silicate minerals rich in iron and magnesium, particularly olivine and pyroxene. Despite being solid, the mantle is not rigid over geological timescales. Over millions of years, the mantle flows slowly through solid-state creep, where crystals deform and atoms migrate through solid material without the rock melting. This flow, driven by heat from Earth's interior, occurs at rates of centimeters per year, fast enough to drive plate tectonics over millions of years, but far too slow to observe directly. The mechanism of solid-state creep involves defects in crystal structures moving through the material, atoms hopping from one lattice site to another, and grains sliding past each other along grain boundaries. At mantle temperatures, close to the melting point, these processes become fast enough to allow flow over geological time. The mantle is further divided into upper and lower mantle. The upper mantle extends from the Moho to about 660 kilometers depth and includes the asthenosphere, a relatively soft, partially molten layer approximately 100-200 kilometers below the surface, where rock is close to its melting point and can flow relatively easily. The asthenosphere's partial melting doesn't mean it's a liquid sea. Typically less than 5% melt exists, with melt distributed as thin films along grain boundaries, but this is enough to significantly reduce strength. The lithosphere, Earth's rigid outer shell comprising the crust and uppermost mantle, floats and moves on top of the asthenosphere. The boundary between lithosphere and asthenosphere is defined thermally rather than compositionally. It's where temperature reaches a critical threshold, allowing easy flow. The lower mantle, from 660 kilometers to 2,900 kilometers depth, is under such immense pressure that the minerals take on denser crystal structures, and the rock, while still technically capable of flowing, is much more viscous than the upper mantle. The boundary at 660 kilometers represents a phase transition where minerals reorganize into denser forms to withstand the pressure. Olivine, the dominant mineral in the upper mantle, transforms through a series of phase changes to denser structures, first to wadsleyite, then to ringwoodite, and finally at 660 kilometers to a mixture of bridgemanite, magnesium silicate perovskite, and ferropriclase. These phase changes are like water transforming to ice. The chemical composition doesn't change, but the crystal structure reorganizes into a denser packing. The 660-kilometer discontinuity is so sharp that some subducting slabs stall there temporarily before eventually sinking into the lower mantle. Beneath the mantle lies the core, beginning at 2,900 kilometers depth and extending to Earth's center at 6,371 kilometers depth. The core is composed primarily of iron, with smaller amounts of nickel and trace amounts of lighter elements like sulfur, oxygen, and silicon. The core is divided into two parts. The outer core, from 2,900 to 5,150 kilometers depth, is liquid. We know this because S-waves from earthquakes don't travel through it. They're absorbed at the core mantle boundary and don't reappear on the opposite side of Earth, creating a shadow zone where S-waves are absent. The liquid outer core is hot, about 4,500 degrees Celsius, but the pressure is not yet high enough to keep the iron solid. The viscosity of the liquid outer core is probably similar to water, very fluid, allowing vigorous convection. The inner core, from 5,150 kilometers to Earth's center, is solid despite being even hotter, approximately 5,205 degrees Celsius, roughly as hot as the sun's surface. At the pressures existing in the inner core, about 3.6 million times atmospheric pressure, iron's melting point is elevated above the actual temperature, causing it to solidify. The inner core is about the size of the moon, a solid sphere of crystalline iron spinning within the liquid outer core, growing slowly over time as the Earth cools and more iron solidifies at the inner core boundary. As iron crystallizes, it releases latent heat and expels lighter elements that don't fit into the iron crystal structure. These lighter elements rise through the liquid outer core, driving convection and contributing to the geodynamo that generates Earth's magnetic field. Recent research suggests the inner core may be more complex than a simple solid sphere. Seismic studies show that seismic waves travel faster through the inner core from north to south than from east to west, suggesting the iron crystals are aligned, possibly due to flow or magnetic fields. There's also evidence for an innermost inner core, a central region about 650 kilometers in radius where the crystal alignment is different, possibly representing a distinct phase of iron or a change in the texture of the solid. The inner core rotates slightly faster than the rest of Earth, gaining about a quarter turn per century, driven by magnetic and gravitational torques from the outer core and mantle. Earth's magnetic field is generated by the liquid iron outer core. Earth possesses a magnetic field that extends tens of thousands of kilometers into space, creating the magnetosphere that shields the surface from the solar wind and cosmic radiation. This magnetic field is not permanent magnetism from iron in the Earth. Temperatures throughout most of Earth's interior far exceed the Curie temperature, above which materials lose permanent magnetization. Iron's Curie temperature is about 770 degrees C, but temperatures in Earth's interior reach thousands of degrees. Instead, Earth's magnetic field is generated by the geodynamo, a self-sustaining process occurring in the liquid outer core. The geodynamo works through a combination of Earth's rotation, convection in the liquid iron outer core, and the conducting properties of molten iron. The liquid outer core is convecting. Hot iron rises from the inner core boundary, cools as it transfers heat to the overlying mantle, and sinks back down. This convection is driven by two sources: thermal convection from heat escaping the core, and compositional convection from light elements released as iron crystallizes onto the inner core. Earth's rotation deflects these convecting currents through the Coriolis effect, creating spiraling, helical flow patterns. As the electrically conducting liquid iron flows through existing magnetic fields, it generates electric currents through electromagnetic induction. These electric currents, in turn, generate new magnetic fields that reinforce and sustain the original fields, creating a self-sustaining dynamo that has operated for at least 3.5 billion years, based on paleomagnetic evidence from ancient rocks. The mathematical description of the geodynamo involves coupled equations for fluid flow and magnetic field evolution, the Navier-Stokes equations for fluid motion, and Maxwell's equations for electromagnetism. These equations are fiercely nonlinear, meaning small changes can lead to large effects, making the system chaotic and the magnetic field unpredictable in detail. Despite decades of work and increasingly sophisticated computer simulations, a complete understanding of the geodynamo remains elusive. Modern simulations can reproduce many features of Earth's magnetic field, including reversals, but they require enormous computational resources and often use simplified physics. Earth's magnetic field is approximately dipolar at Earth's surface, similar to the field that would be produced by a giant bar magnet tilted about 11 degrees from Earth's rotation axis. The field lines emerge from near the south geographic pole, where the north magnetic pole is located. Magnetic poles are defined by the direction compass needles point, which points north toward the north magnetic pole, confusingly located near the south geographic pole. Field lines curve through space and re-enter near the north geographic pole. However, the field is not perfectly dipolar. There are regional variations and irregularities, and the field shape changes over time. The magnetic poles wander slowly, moving several to tens of kilometers per year. Currently, the North Magnetic Pole is moving from northern Canada towards Siberia at an accelerating rate, traveling about 55 kilometers per year, compared to about 15 kilometers per year a century ago. The cause of this acceleration isn't fully understood, but likely reflects changes in flow patterns deep in the outer core. More dramatically, Earth's magnetic field occasionally reverses polarity completely. The north and south magnetic poles swap positions. These reversals occur irregularly, sometimes just tens of thousands of years apart, sometimes millions of years apart. The last reversal, the Brunhes-Matayama reversal, occurred about 780,000 years ago. On average, reversals occur roughly every 200,000 years, but the timing is highly variable. During the Cretaceous period, there was a long period called the Cretaceous normal superchron, lasting about 40 million years with no reversals. The current normal polarity has lasted 780,000 years, longer than the average, leading some to speculate a reversal may be overdue, though the timing is fundamentally unpredictable. The reversal process takes 1,100 years, during which the field weakens, becomes more complex with multiple poles, and eventually reestablishes in the opposite polarity. During reversals, the field doesn't disappear completely, but becomes weaker and more complex, potentially allowing more solar wind particles and cosmic rays to reach the atmosphere. Whether reversals have caused biological extinctions is debated. The evidence is mixed, and organisms have clearly survived hundreds of reversals over Earth's history. Some researchers propose that magnetic reversals coincide with extinctions or evolutionary changes, possibly due to increased radiation exposure. But the correlations are weak, and other explanations often more plausible. The paleomagnetic record of reversals is preserved in rocks, particularly in oceanic crust forming at mid-ocean ridges. As lava erupts and cools below the Curie temperature, iron-bearing minerals align with Earth's magnetic field like tiny compass needles and lock in place as the rock solidifies, recording the field direction at the time. As seafloor spreading creates new crust on either side of the ridge, the magnetic alignment alternates between normal and reversed polarity with each field reversal, creating symmetric stripes of alternating polarity parallel to the ridge. These magnetic stripes, discovered in the 1960s, provided some of the most compelling evidence for seafloor spreading and plate tectonics, and the pattern of reversals has been used to calibrate the geomagnetic timescale, allowing dating of oceanic crust and correlation of geological events globally. The reversal chronology now extends back over 160 million years from oceanic crust and much further from continental rocks and marine magnetic anomalies. Plate tectonics is the theory that Earth's lithosphere is divided into moving plates. Earth's rigid outer shell, the lithosphere, is broken into about a dozen major plates and several smaller ones. These plates move relative to one another at rates of centimeters per year, driven by forces ultimately rooted in heat escaping from Earth's interior. The theory of plate tectonics developed primarily in the 1960s, though building on earlier continental drift ideas proposed by Alfred Wegener in 1912, revolutionized Earth science by providing a unifying framework explaining earthquakes, volcanoes, mountain building, and the distribution of fossils and rock types globally. Alfred Wegener proposed continental drift in 1912 based on multiple lines of evidence. The jigsaw fit of continents, particularly South America and Africa, identical fossil species on continents now separated by oceans, similar rock sequences and mountain belts on different continents, and evidence of ancient glaciation in now tropical regions. Wegener argued that continents once formed a single supercontinent, which he called Pangaea, that broke apart and drifted to present positions. His ideas were initially rejected because he couldn't explain what force could move continents through oceanic crust. Geophysicists calculated that no known force was strong enough. The breakthrough came decades later with the discovery of seafloor spreading and the realization that continents don't plow through oceanic crust, but rather are carried passively as part of larger lithospheric plates. Three types of plate boundaries exist. Divergent boundaries occur where plates move apart. As plates separate, the lithosphere stretches and thins, and magma from the underlying asthenosphere rises to fill the gap, creating new crust. Most divergent boundaries are mid-ocean ridges, underwater mountain ranges where seafloor spreading occurs. The Mid-Atlantic Ridge, running down the center of the Atlantic Ocean from the Arctic to near Antarctica, is the longest mountain range on Earth, over 16,000 kilometers long, formed as the Eurasian and North American plates separate to the north, and the African and South American plates separate to the south. The spreading rate varies. The East Pacific rise spreads at 616 centimeters per year, fast spreading, while the Mid-Atlantic Ridge spreads at only 2-3 centimeters per year, slow spreading. Iceland sits directly on the Mid-Atlantic Ridge, one of the few places where a mid-ocean ridge rises above sea level. allowing direct observation of seafloor spreading processes that normally occur kilometers underwater. At mid-ocean ridges, the topography and volcanic style differ depending on spreading rate. Fast-spreading ridges like the East Pacific Rise have smooth topography with a low, broad rise and a small central valley. The magma supply is steady, and eruptions fill the rift zone continuously. Slow-spreading ridges like the Mid-Atlantic Ridge have rougher topography with a deep rift valley, steep flanks, and episodic volcanism. The difference reflects the balance between magma supply and plate separation rate. The East African Rift Valley is a continental divergent boundary where Africa is beginning to split apart. In millions of years, if spreading continues, the rift will widen into a new ocean basin, and Eastern Africa will separate as a new continent or large island. Convergent boundaries occur where plates move toward one another. If an oceanic plate collides with a continental plate, the denser oceanic plate subducts beneath the lighter continental plate, descending into the mantle. As the oceanic plate descends, water trapped in sediments and altered oceanic crust is released, lowering the melting point of the overlying mantle wedge and causing partial melting. The magma, less dense than surrounding rock, rises and eventually erupts at the surface, creating a volcanic arc parallel to the subduction zone. The Cascade Range in the Pacific Northwest, including Mount St. Helens, which erupted catastrophically in 1980, and Mount Rainier, which poses a potential hazard to the Seattle-Tacoma region, formed this way as the Juan de Fuca Plate subducts beneath the North American Plate. The Andes Mountains in South America are another example, formed by subduction of the Nazca Plate beneath the South American Plate, creating the longest continental mountain range on Earth, stretching over 7,000 kilometers. If two oceanic plates converge, one subducts beneath the other, creating a deep ocean trench at the boundary and a volcanic island arc on the overriding plate. The Mariana Trench, the deepest part of the ocean at nearly 11,000 meters deep, formed where the Pacific Plate subducts beneath the smaller Mariana Plate, and the Mariana Islands themselves are the volcanic arc. Japan, the Philippines, and Indonesia are all island arcs formed by oceanic-oceanic convergence. The subducting plate in these settings descends at steep angles, sometimes nearly vertical, and can be traced seismically to depths of 600–700 kilometers before it loses its seismic signature, presumably because it warms and integrates into the surrounding mantle. When two continental plates collide, neither subducts easily because continental crust is too buoyant. Instead, the crust crumples and thickens, building high mountain ranges. The Himalayas, Earth's highest mountains, are forming as the Indian Plate collides with the Eurasian Plate, a collision that began about 50 million years ago and continues today. The Indian Plate is still moving northward at about 5 centimeters per year, and the Himalayas continue rising, though erosion simultaneously wears them down. The collision has doubled the crustal thickness beneath Tibet, creating the Tibetan Plateau, the highest and largest plateau on Earth with an average elevation over 4,500 meters. The collision has also affected areas far from the boundary. The stress is transmitted through the Eurasian Plate, causing earthquakes and faulting deep in Asia's interior. Transform boundaries occur where plates slide horizontally past one another. The San Andreas Fault in California is a transform boundary where the Pacific Plate slides northwestward relative to the North American Plate at about 5 centimeters per year. Transform boundaries don't create or destroy crust, but accommodate the differential motion of plates. often generating powerful earthquakes as plates lock and then suddenly slip. The 1906 San Francisco earthquake occurred when about 300 kilometers of the San Andreas Fault slipped as much as 6 meters in seconds, releasing accumulated stress. Transform faults also occur along mid-ocean ridges, offsetting the ridge axis and accommodating variations in spreading rate. These transform faults are among the most seismically active features on Earth, generating frequent small to moderate earthquakes. The driving mechanisms of plate tectonics involve multiple forces. Slab pull is thought to be the most important. As dense oceanic lithosphere subducts into the mantle, gravity pulls the plate downward, dragging the rest of the plate along. Studies measuring plate velocities show that plates with large subducting slabs move faster than plates without, supporting slab pull's importance. Ridge push contributes. The elevated topography of mid-ocean ridges creates gravitational potential energy, pushing plates away from the ridge. Mantle convection, the underlying heat-driven flow in the mantle, provides the ultimate energy source and may actively drag plates to some degree, though the exact coupling between mantle flow and plate motion remains debated. Some regions show good correlation between plate motion and underlying mantle flow inferred from seismic tomography. Other regions show poor correlation, suggesting complex interactions. Plate tectonics is ultimately a heat engine, with Earth's internal heat, derived from primordial heat left over from formation plus heat, continuously generated by radioactive decay of uranium, thorium, and potassium in the crust and mantle, driving the motion. Earth's heat production has declined over geological time as radioactive isotopes decayed. Heat production was perhaps 3 times higher 4 billion years ago than today. As Earth cools over billions of years, plate tectonic activity may gradually slow, though this timescale is many billions of years in the future. Eventually, perhaps in a few billion years, Earth's interior may cool enough that plate tectonics ceases, as appears to have happened on Mars and Venus, though Venus may have episodic resurfacing events. At that point, Earth would become a stagnant lid planet like Mars, with a solid lithosphere covering the entire planet and no plate motions. Earth's atmosphere is about 78% nitrogen and 21% oxygen. The atmosphere is a thin envelope of gases held to Earth by gravity, extending from the surface to gradually thinning air that blends into space. Most of the atmosphere's mass, about 75%, lies within the lowest 11 kilometers, the troposphere, where weather occurs. About 99% of atmospheric mass lies below 32 kilometers. The composition by volume of dry air is approximately 78% nitrogen, 21% oxygen, 0.93% argon, 0.04% carbon dioxide, and trace amounts of neon, helium, methane, krypton, and hydrogen. Water vapor is highly variable, ranging from near zero in cold, dry locations to about 4% in warm, humid tropical areas. This composition is dramatically different from the atmospheres of our neighboring planets. Venus and Mars have atmospheres over 95% carbon dioxide, with virtually no oxygen, and Earth's high oxygen content is a direct result of life. Earth's atmosphere has undergone radical changes over geological time. The earliest atmosphere, if any survived the moon-forming impact, was likely lost, and the subsequent early atmosphere was probably a reducing atmosphere rich in hydrogen, helium, methane, ammonia, and water vapor, outgassed from volcanic activity and delivered by impacting comets and asteroids. Free oxygen was essentially absent. Early Earth's atmosphere probably resembled the atmospheres of the outer planets' moons like Titan, with nitrogen, methane, and hydrogen compounds. The absence of oxygen meant no ozone layer, so ultraviolet radiation from the sun reached the surface unimpeded, providing energy that may have facilitated prebiotic chemistry, but also created a harsh environment for any early life. This changed dramatically with the evolution of photosynthesis. Cyanobacteria, among Earth's earliest organisms, evolved the ability to use sunlight to split water molecules, releasing oxygen as a waste product. This oxygenic photosynthesis, different from the earlier anaxigenic photosynthesis that some bacteria still use, was revolutionary. For hundreds of millions of years, the oxygen produced was consumed by reacting with dissolved iron in the oceans, precipitating vast iron deposits called banded iron formations that preserve a record of this transition. These formations, composed of alternating layers of iron-rich and iron-poor minerals, are among the world's major iron ore deposits, and they tell a story of rising oxygen levels. As cyanobacteria produced oxygen, it reacted with iron dissolved in seawater, precipitating iron oxides that settled to the seafloor. When local iron was depleted, oxygen could temporarily accumulate until ocean circulation delivered more iron-rich water, creating the banded pattern. Eventually, about 2.4 billion years ago, oxygen began accumulating in the atmosphere in what's called the Great Oxidation Event, or oxygen catastrophe. The rise in atmospheric oxygen had profound consequences. For organisms that had evolved in an oxygen-free world, oxygen was toxic. It generates reactive oxygen species that damage biomolecules. The oxygenation may have caused mass extinctions of organisms that couldn't adapt. Methane, which had been a significant greenhouse gas in the early atmosphere, reacted with oxygen and was removed, possibly causing severe global cooling and snowball Earth conditions. But oxygen also enabled new forms of metabolism. Aerobic respiration, using oxygen to extract energy from organic molecules, is far more efficient than anaerobic metabolism, providing enough energy to support complex, multicellular organisms. The rise of oxygen enabled the eventual evolution of animals. Oxygen levels have fluctuated over geological time, reaching perhaps 35% in the Carboniferous period, about 300 million years ago, when vast forests buried carbon that wasn't decomposed as quickly as it is today, allowing oxygen to accumulate. These high oxygen levels may have enabled the evolution of gigantic insects, dragonflies with 70-centimeter wingspans and millipedes over a meter long, which relied on passive diffusion of oxygen through their bodies via tracheal systems, only feasible when atmospheric oxygen was higher. The current atmospheric composition is maintained by complex interactions between life, geology, and chemistry. Oxygen is continuously consumed by respiration, combustion, and reaction with rocks, but continuously replenished by photosynthesis. Carbon dioxide is removed by photosynthesis and by dissolving in ocean water, where it forms carbonic acid and eventually precipitates as carbonate minerals. But it's continuously released by respiration, decay, volcanic activity, and dissolution of carbonate rocks. These cycles operate on vastly different timescales. The biological carbon cycle turns over in years to centuries, while the geological carbon cycle operates over hundreds of thousands to millions of years. The relative stability of atmospheric composition over millions of years suggests regulatory feedbacks maintain it, though the mechanisms are complex and not fully understood. The biological and geological cycles interact. Life affects the composition of rocks and minerals, and geological processes affect the availability of nutrients for life. The atmosphere's pressure and temperature decrease with altitude in a series of layers. The troposphere from the surface to about 11 kilometers at mid-latitudes, higher at the equator around 16-18 kilometers, lower at poles around 8 kilometers, is where temperature decreases with altitude due to decreasing air pressure, and where virtually all weather occurs. Air pressure decreases exponentially with altitude. At 5.6 kilometers elevation, pressure is half that at sea level. Temperature decreases at an average rate of about 5 degrees C per kilometer in the troposphere, though the actual rate varies depending on humidity and other factors. The tropopause, the boundary between troposphere and stratosphere, marks where temperature stops decreasing with altitude. Commercial aircraft typically fly at the tropopause or in the lower stratosphere to avoid weather and benefit from lower air resistance. The stratosphere, from about 11 to 50 kilometers, is where temperature increases with altitude due to absorption of ultraviolet radiation by ozone. The ozone layer, concentrated at 20-30 kilometers altitude, absorbs harmful UV radiation, protecting life on Earth's surface and heating the stratosphere through this absorption. Without the ozone layer, surface UV levels would be much higher, increasing mutation rates and potentially making land colonization by life more difficult. The discovery of the Antarctic ozone hole in the 1980s, caused by chlorofluorocarbons, CFCs, from human activities, led to the Montreal Protocol, one of the most successful international environmental agreements, which phased out CFCs. The ozone layer is now recovering, expected to return to 1980 levels by mid-century, though Antarctic ozone still shows significant seasonal depletion each spring. The mesosphere from 50 to 85 kilometers sees temperature again decreasing with altitude, reaching the coldest atmospheric temperatures as low as degrees C at the mesopause. This is where meteors burn up, creating visible shooting stars. The mesosphere is difficult to study. It's too high for aircraft and balloons, too low for satellites, requiring sounding rockets for direct measurement. The thermosphere, above 85 kilometers, is where temperature increases dramatically with altitude, reaching over 1000 degrees C, though the air is so thin that you'd actually freeze quickly because there's so little air to conduct heat to you. The International Space Station orbits in the thermosphere at around 400 kilometers altitude. The aurora occur in the thermosphere as charged particles from the solar wind collide with atmospheric atoms. The exosphere, above about 500 kilometers, gradually transitions to the vacuum of space, with molecules so sparse that they can travel kilometers without colliding. Satellites in the exosphere experience essentially no atmospheric drag, allowing stable orbits for many years. The boundary between Earth's atmosphere and space is arbitrary. There's no sharp edge. The Kármán line at 100 kilometers altitude is often used as the conventional boundary because above this altitude, aerodynamic flight becomes impossible and orbital mechanics dominate. But particles of Earth's atmosphere extend much higher, forming a tenuous geocorona of hydrogen atoms extending tens of thousands of kilometers. Water covers approximately 71% of Earth's surface. Of Earth's total surface area, of 510 million square kilometers, oceans cover about 361 million square kilometers. The Pacific Ocean alone covers about 165 million square kilometers, more than all land areas combined. The average depth of the ocean is about 3,688 meters, with the deepest point, the Challenger Deep in the Mariana Trench, reaching approximately 10,994 meters, measured by direct descent in 2019 to 10,925 meters, plus water depth measurements. If Earth's solid surface were perfectly smooth without mountains or ocean trenches, water would cover the entire planet to a depth of about 2,700 meters. Earth is predominantly a water world, and the existence of dry land depends on the uneven distribution of elevation. The total volume of water in Earth's oceans is approximately 1.335 billion cubic kilometers. This seems vast, but if you collected all Earth's water into a sphere, it would be only about 1,385 kilometers in diameter, small compared to Earth's 12,742 kilometer diameter. Despite covering most of Earth's surface, water makes up only about 0.02% of Earth's total mass. Most water is in the oceans, about 97%, with smaller amounts in ice caps and glaciers, about 2%, roughly 24 million cubic kilometers, groundwater, about 0.6%, and tiny fractions in lakes, rivers, soil moisture, atmosphere, and living organisms. The small fraction in ice caps represents an enormous volume. If all ice melted, sea level would rise approximately 70 meters, flooding coastal cities worldwide and redrawing maps to show coastlines far inland from their current positions. The origin of Earth's water is debated. Water is a simple molecule, two hydrogen atoms bonded to one oxygen atom, but hydrogen, while abundant in the early solar nebula, is so light it easily escapes rocky planets. Where did Earth get its water? Some may have been present in the rocky materials that accreted to form Earth, bound in hydrated minerals, and released through volcanic outgassing as the planet heated. Volcanic eruptions today release water vapor along with other gases, and this outgassing over billions of years could have supplied some of Earth's water. But isotopic analysis suggests this can't account for all of Earth's water. The deuterium to hydrogen ratio, DH ratio, a key isotopic fingerprint in water from Earth's oceans, differs from that in the solar nebula and from most meteorites, providing clues about water's origin. Another source was impacts by water-rich asteroids and comets during and after Earth's formation. Carbonaceous chondrite asteroids, primitive bodies rich in water and organic compounds, have DH ratios similar to Earth's oceans, suggesting they may be the dominant source. These asteroids likely delivered much of Earth's water during the period of heavy bombardment in the first few 100 million years after Earth formed. Comets also contain abundant water, but isotopic measurements of comets show most have DH ratios higher than Earth's oceans, suggesting comets contributed less water than once thought, though sample sizes are small. We've measured only a few comets directly, and more measurements are needed. Some comets, particularly Jupiter family comets that originate from the Kuiper Belt, have DH ratios closer to Earth's, leaving open the possibility that certain comet populations contributed significantly. Whenever it arrived, water has been crucial to making Earth habitable. Water is an excellent solvent, dissolving a wide range of substances and enabling the chemistry of life. Biochemical reactions occur in aqueous solution, and water's properties facilitate molecular interactions essential to life. Water has high heat capacity, moderating temperatures by absorbing and releasing heat slowly, preventing rapid temperature swings. Oceans store enormous amounts of heat, warming coastal areas in winter and cooling them in summer. Water's solid form, ice, is less dense than liquid water, an unusual property. Most substances are denser in solid form. Ice floats. This prevents bodies of water from freezing solid from the bottom up, as would happen if ice were denser. Instead, ice forms on the surface, insulating deeper water and allowing aquatic life to survive winters. Lakes and oceans freeze from the top down, maintaining liquid water below even in harsh winters. Water's surface tension, hydrogen bonding, and other properties create unique environments that life exploits. Surface tension allows small organisms to walk on water. Capillary action draws water up plant roots and through soil. Water's high latent heat of vaporization means evaporation consumes significant energy, cooling surfaces. Sweating works because evaporating water carries away heat. Water is transparent to visible light, but absorbs infrared radiation, allowing photosynthesis in aquatic environments while absorbing heat. These properties, taken together, make water uniquely suited to supporting life as we know it, though whether other solvents could support life in different conditions remains an open question in astrobiology. The water cycle continuously moves water between ocean, atmosphere, and land. The sun's energy evaporates water from oceans, lakes, and soil, about 505,000 cubic kilometers per year globally. Plants transpire water through their leaves, adding to atmospheric water. A single tree can transpire hundreds of liters per day in hot conditions. Water vapor rises, cools, and condenses into clouds. Clouds transport water vapor, driven by atmospheric circulation. Eventually, water precipitates as rain or snow, falling to land or ocean. Precipitation on land flows in rivers back to the ocean, infiltrates into groundwater, is absorbed by plants, or evaporates. The cycle has no beginning or end, but represents continuous circulation, with individual water molecules spending varying amounts of time in different reservoirs. Water molecules in the atmosphere have a residence time of about 9 days, in rivers about 2 weeks, in soil moisture a few months to a year, in glaciers thousands of years, in groundwater years to millennia depending on depth, and in deep ocean water centuries to millennia. Ocean water is salty, with an average salinity of about 35 parts per thousand, meaning each kilogram of seawater contains about 35 grams of dissolved salts, primarily sodium chloride, but also magnesium, sulfate, calcium, and potassium. Salinity varies regionally. Near river mouths, freshwater dilutes seawater, reducing salinity to 25–30 parts per thousand or less. In enclosed seas with high evaporation like the Red Sea or Mediterranean, salinity reaches 40 parts per thousand or higher. In the Dead Sea, where evaporation vastly exceeds freshwater input, and the sea is in a closed basin with no outlet, salinity reaches 340 parts per thousand, nearly 10 times ocean salinity, making the water dense enough to effortlessly float a person. Salinity, along with temperature, determines seawater density, which drives ocean circulation. Cold, salty water is denser and sinks, driving deep ocean currents. The global thermohaline circulation, a slow overturning of the entire ocean taking about 1,000 years to complete one cycle, transports heat from equator to poles and brings nutrients from deep water to the surface, playing crucial roles in climate and marine ecosystems. Surface currents, driven by winds and modified by Coriolis effect and continental boundaries, move water horizontally across ocean basins. Deep currents, driven by density differences, move water vertically and horizontally through the ocean interior, ventilating the deep ocean with oxygen from the surface and redistributing heat and nutrients globally. Earth's climate is driven by uneven solar heating and moderated by oceans and atmosphere. The sun is Earth's primary energy source, delivering about 1,361 watts per square meter to the top of the atmosphere on average, though the actual amount varies with latitude, season, and time of day. This number, called the solar constant, actually varies slightly with Earth's orbital distance and with solar activity, but it averages around 1,361 Wm2. The equator receives far more solar energy per unit area than the poles because sunlight strikes the equator nearly perpendicularly, concentrating energy, while at high latitudes, sunlight arrives at a low angle, spreading the same energy over a larger area. Additionally, sunlight at high latitudes must travel through more atmosphere, where some is absorbed or reflected. This uneven heating, tropical regions receiving more energy than they radiate back to space, polar regions radiating more than they receive, drives atmospheric and ocean circulation that transports heat from equator to poles, moderating temperatures globally and making much of Earth habitable. Atmospheric circulation organizes into relatively stable patterns. Near the equator, intense solar heating warms air, causing it to rise. Rising air expands and cools adiabatically without exchanging heat with surroundings, and as it cools, its capacity to hold water vapor decreases, causing condensation and precipitation. This is why tropical regions are so wet, receiving over 2,000 millimeters of rain annually in many areas. The Intertropical Convergence Zone, ITCZ, where northeast and southeast trade winds meet, is a band of intense precipitation encircling the equator, shifting north and south seasonally following the sun's most direct rays. The rising air flows poleward at high altitude, cools and descends at about 30 degrees latitude north and south, creating high-pressure zones with dry, clear conditions. This is where most of the world's deserts, including the Sahara, Arabian, Kalahari, and Australian deserts, form. The descending air flows along the surface both back toward the equator, the trade winds, and toward the poles, the westerlies. This creates circulation cells called Hadley cells in the tropics. Similar circulation cells, the Ferrel cells and polar cells, exist at higher latitudes, though they're less well-defined. Ferrel cells, in mid-latitudes between about 30 and 60 degrees, are driven partly by the Hadley and polar cells and partly by instabilities and eddies. Polar cells occur at high latitudes, with cold air descending at the poles and flowing toward mid-latitudes. These cells organize global wind patterns and influence where precipitation occurs and where deserts form. The boundaries between cells are zones of changeable weather. The mid-latitude boundary between ferrel and polar cells, where the polar front jet stream forms, is a zone of storms and variable weather familiar to people in North America, Europe, and Asia. Earth's rotation deflects moving air through the Coriolis effect, causing winds to curve rather than flow directly north or south. In the northern hemisphere, winds deflect to the right, in the southern hemisphere to the left. This creates the prevailing wind patterns, trade winds blowing from northeast to southwest in the northern hemisphere tropics, and from southeast to northwest in the southern hemisphere tropics. westerlies blowing from southwest to northeast in the northern hemisphere mid-latitudes, and from northwest to southeast in the southern hemisphere, and polar easterlies at high latitudes. These wind patterns have historically shaped human exploration, trade routes, and climate patterns. Sailors in the age of exploration used trade winds to cross the Atlantic and Pacific, and understanding global wind patterns was crucial for navigation and commerce. Ocean currents transport heat even more efficiently than atmospheric circulation because water has higher heat capacity than air. Moving water carries far more heat energy than moving air at the same temperature. Surface currents are driven primarily by winds and deflected by the Coriolis effect and by continental boundaries, creating large circular gyres in each ocean basin, clockwise in the northern hemisphere, counterclockwise in the southern hemisphere. Western boundary currents like the Gulf Stream, Kuroshio Current, Brazil Current, and Agulhas Current are particularly strong and narrow, carrying warm water from the tropics toward the poles. Eastern boundary currents like the California Current and Peru Current are weaker and broader, carrying cool water from higher latitudes toward the equator. The Gulf Stream transports about 30 spheredrups of water. 1 spheredrup equals 1 million cubic meters per second, about 30 times more water than all the world's rivers combined, moving warm water from the Gulf of Mexico across the Atlantic toward northwestern Europe, moderating the climate significantly. London, at 51 degrees N latitude, has a much milder climate than Labrador at the same latitude on the western side of the Atlantic, with winter temperatures often 20–30 degrees C warmer, because the Gulf Stream and North Atlantic Drift carry warm water to Europe. Without this heat transport, much of northern Europe would be far colder, potentially limiting agriculture and habitability. Deep ocean currents, driven by density differences, form the thermohaline circulation, sometimes called the ocean conveyor belt. In the North Atlantic, the Gulf Stream carries warm, salty water northward. As it releases heat to the atmosphere, warming northwestern Europe, the water cools. Cold, salty water is very dense and sinks in the Norwegian and Greenland seas, forming North Atlantic deep water, NADW. This water flows southward at depth, through the Atlantic, around Antarctica where it mixes with Antarctic bottom water, AABW, the densest water in the ocean formed around Antarctica, and into the Indian and Pacific Oceans. Eventually, this deep water gradually mixes upward through diffusion and upwelling, returns to the surface in the Pacific and Indian Oceans, and flows back toward the Atlantic at the surface in a global conveyor belt pattern that takes roughly 1,000 years to complete. This circulation distributes heat globally and ventilates the deep ocean with oxygen from the surface. Changes in this circulation, potentially caused by freshwater input from melting ice sheets, reducing surface salinity and preventing sinking, could significantly alter global climate. Evidence suggests rapid climate changes in the past were associated with thermohaline circulation disruptions. The greenhouse effect is crucial to Earth's climate. Solar radiation, primarily in visible wavelengths where the sun emits most strongly, passes through the atmosphere relatively unimpeded and is absorbed by Earth's surface, warming it. The warm surface radiates energy back towards space, but this radiation is in infrared wavelengths because Earth's surface is much cooler than the sun, and objects radiate at wavelengths determined by their temperature. Greenhouse gases in the atmosphere, water vapor, carbon dioxide, methane, nitrous oxide, ozone, and others, absorb infrared radiation. The molecular structure of these gases allows them to vibrate in ways that interact with infrared photons. These molecules re-radiate the energy in all directions, including back toward the surface, warming it further. Without the greenhouse effect, Earth's average surface temperature would be about -18 degrees C, and the oceans would be frozen. With the current greenhouse effect, the average temperature is about 15 degrees C. Greenhouse gases thus make Earth habitable, but increasing their concentrations enhances the greenhouse effect, raising temperatures. This is the mechanism behind current climate change, as human activities increase atmospheric CO2 from about 280 parts per million before industrialization to over 420 parts per million today, a 50% increase. The greenhouse effect is not a simple blanket warming, but involves complex feedbacks. Water vapor is the most important greenhouse gas by total effect, but its atmospheric concentration is determined by temperature. Warmer air holds more water vapor. As CO2 increases and warms the planet, atmospheric water vapor increases, amplifying warming in a positive feedback. Clouds have complex effects. Low clouds reflect sunlight, cooling the surface, while high clouds trap infrared radiation, warming it. Ice and snow reflect sunlight, so as warming melts ice, darker ocean and land are exposed, absorbing more sunlight and causing additional warming in another positive feedback called ice albedo feedback. These feedbacks make climate sensitive to changes in greenhouse gas concentrations, meaning small changes in forcing can produce large changes in temperature over time as feedbacks amplify the initial perturbation. Life has existed on Earth for at least 3.5 billion years. The earliest evidence of life comes from stromatolites, layered structures created by communities of microorganisms, particularly cyanobacteria, found in rocks approximately 3.5 billion years old in Western Australia. Stromatolites form when microbial mats trap and bind sediment, building up in layers over time. Living stromatolites still exist today in a few locations like Shark Bay, Australia, providing analogues for understanding ancient forms and showing that this mode of microbial growth has persisted for billions of years. The ancient stromatolites from Western Australia are controversial. Some scientists question whether they're truly biological or might be abiotic structures formed by geological processes. But the consensus among most researchers is that they represent genuine evidence of early life, supported by carbon isotope ratios and microscopic structures consistent with biological origin. Even older potential evidence exists. Carbon isotope ratios in rocks up to 3.8 or possibly 4.1 billion years old may reflect biological processing, though this interpretation is debated because abiotic processes can sometimes produce similar signatures. Biological systems preferentially use the lighter carbon isotope, carbon-12, over carbon-13, creating a characteristic isotopic signature in organic matter. Finding this signature in ancient rocks suggests life was present, but it's not definitive proof because certain non-biological processes can fractionate carbon isotopes similarly. Additionally, these ancient rocks have often been metamorphosed, potentially altering isotopic signatures and complicating interpretation. Life likely originated much earlier than 3.5 billion years ago, perhaps around 3.84 billion years ago, when the surface had cooled enough for liquid water to exist stably. Though the late heavy bombardment, a period of intense asteroid and comet impacts ending about 3.8 billion years ago, may have made the surface inhospitable, possibly destroying earlier life if it had emerged or forcing it to survive only in protected subsurface environments. During the late heavy bombardment, Some impacts were large enough to vaporize the oceans temporarily, sterilizing the surface, but potentially leaving subsurface life intact. Life might have emerged multiple times, only to be wiped out by large impacts before finally establishing permanently. How life originated remains one of science's greatest unsolved questions. Life requires replicating molecules that can evolve, metabolism to extract and use energy, and some form of compartmentalization to separate internal chemistry from the environment. Modern life uses DNA for information storage, RNA for information transfer and sometimes catalysis, and proteins for most catalytic functions and structural roles, all enclosed in lipid membranes. But DNA, RNA, and proteins are complex molecules that require sophisticated cellular machinery to synthesize. How did this system arise? This is a chicken and egg problem. DNA requires proteins, enzymes, to replicate, but proteins require DNA genes to specify their structure. The RNA world hypothesis proposes that early life used RNA for both information storage and catalysis, since RNA can do both, whereas DNA stores information but doesn't catalyze reactions, and proteins catalyze reactions but don't store information. RNA could have been the original self-replicating molecule, with DNA and proteins evolving later as the system became more sophisticated. Supporting this, some modern enzymes use RNA catalysts, ribozymes, and the ribosome, which synthesizes proteins in all modern cells, uses RNA as the catalyst. The peptidyl transferase activity that forms peptide bonds is performed by ribosomal RNA, not protein. But even RNA is complex. How did it form abiotically? Laboratory experiments show that building blocks of RNA, including ribose sugar and nucleotide bases like adenine and guanine, can form under prebiotic conditions simulating early Earth, though assembling them into RNA polymers remains challenging. Recent research has made progress, showing that wet-dry cycles, freeze-thaw cycles, and mineral surfaces can facilitate polymerization, but a complete pathway from simple molecules to self-replicating RNA hasn't been demonstrated in the laboratory. Where did life originate? One hypothesis is tide pools or shallow water where evaporation could concentrate organic molecules. UV light could drive reactions, and wet-dry cycles could facilitate polymer formation. Darwin speculated about a warm little pond, though he recognized this was highly speculative. Another hypothesis is deep-sea hydrothermal vents, where hot, mineral-rich water emerges from the seafloor. These environments provide chemical energy from reactions between minerals and water, reducing conditions that favor formation of organic molecules and mineral surfaces that might catalyze reactions. Modern hydrothermal vents support rich ecosystems based on chemosynthesis rather than photosynthesis, showing that life can thrive in these environments, though whether life originated there is unknown. Submarine alkaline vents, which produce gradients in pH and redox potential similar to those that power modern cells, are particularly promising candidates. These vents form where seawater reacts with rocks in a process called serpentinization, producing hydrogen and creating alkaline, warm fluids that mix with acidic seawater, generating pH gradients and minerals with porous structures that could serve as natural compartments. The proton gradients produced resemble the proton gradients that cells use to generate ATP, suggesting these environments might have provided free energy, that protocells could exploit before they evolved mechanisms to generate such gradients themselves. Another possibility is that life's building blocks formed elsewhere and arrived on Earth via meteorites or comets. Organic molecules, including amino acids, nucleobases, sugars, and amphiphiles that can form membrane-like structures, have been found in carbonaceous meteorites, showing that prebiotic chemistry can occur in space. Whether this contributed significantly to life's origin is debated. Delivering intact complex molecules requires that they survive the heat and shock of entering Earth's atmosphere and impacting the surface. Some molecules would be destroyed, but some could survive, particularly in larger impactors where interior material is protected. Regardless, even if building blocks arrived from space, they still needed to be assembled into living systems, which required conditions on Earth. So this doesn't solve the origin of life problem, but rather shifts where some prebiotic chemistry occurred. However it originated, early life was simple, probably consisting of single cells lacking nuclei, prokaryotes like modern bacteria and archaea. For roughly 2 billion years, prokaryotes were the only life on Earth, evolving diverse metabolisms including photosynthesis, which would eventually transform the planet. The earliest photosynthesis was probably anexigenic, using electron donors other than water, hydrogen sulfide, ferrous iron, hydrogen, and not producing oxygen, similar to how some bacteria today perform photosynthesis. Oxygenic photosynthesis, using water as electron donor and releasing oxygen, evolved later, probably in cyanobacteria. This was revolutionary because water is abundant, unlike other electron donors, allowing photosynthetic organisms to thrive almost anywhere sunlight reaches. About 2.4 billion years ago, cyanobacteria began producing oxygen through oxygenic photosynthesis, gradually oxygenating the atmosphere in the Great Oxidation Event. This enabled the eventual evolution of eukaryotes, cells with nuclei and complex internal structures, which appeared about 2 billion years ago, probably through symbiotic mergers of prokaryotes. Mitochondria, the energy-producing organelles in eukaryotic cells, were once free-living bacteria that were engulfed and incorporated, probably an alpha protobacterium that became an endosymbiont. Chloroplasts, the photosynthetic organelles in plants and algae, were cyanobacteria similarly incorporated. These endosymbiotic events are supported by multiple lines of evidence. Mitochondria and chloroplasts have their own DNA, distinct from nuclear DNA and similar to bacterial DNA. They reproduce independently within cells by division. They have double membranes consistent with being engulfed, and their ribosomes resemble bacterial ribosomes. Multicellular life didn't appear until about 600 million years ago, in the Ediacaran period, when strange, soft-bodied organisms of uncertain relationships to modern groups appeared, including frond-like forms, quilted structures, and disc-shaped organisms. The Cambrian explosion, about 541 million years ago, saw the rapid appearance of most major animal groups within about 20-30 million years, a geological eye blink. During the Cambrian, animals evolved hard shells, skeletons, sophisticated eyes, and diverse body plans. The Cambrian explosion may have been enabled by rising oxygen levels reaching thresholds needed to support active, complex animals, by ecological interactions including predation creating evolutionary arms races, and by genetic innovations including evolution of developmental genes, Hox genes, allowing more complex body plans. Life colonized land about 470 million years ago with plants, followed by arthropods, then vertebrates. The transition to land required numerous adaptations: waterproofing to prevent desiccation, structural support against gravity without water's buoyancy, methods to obtain water and nutrients from soil rather than absorbing them from surrounding water, and reproduction in dry conditions. The dinosaurs dominated terrestrial ecosystems for about 165 million years during the Mesozoic era, before most were wiped out 66 million years ago by an asteroid impact. Mammals, which had existed in the shadow of dinosaurs as mostly small, nocturnal insectivores, diversified explosively after the extinction, filling ecological niches vacated by dinosaurs. Primates evolved about 55 million years ago, and the human lineage split from chimpanzees about 6-7 million years ago. Anatomically modern humans, Homo sapiens, emerged about 300,000 years ago in Africa, an eye blink in Earth's 4.5 billion year history, yet we've become a geological force, reshaping the planet. Earth has experienced 5 major mass extinctions in the past 500 million years. Mass extinctions are periods when exceptionally high percentages of species went extinct in geologically short periods. The definition is somewhat arbitrary, but 5 events in the Phanerozoic, the past 541 million years, when hard-bodied animals became common and fossils abundant, stand out as the Big Five. The Ordovician-Silurian extinction, about 445 million years ago, killed approximately 85% of marine species in 2 pulses separated by hundreds of thousands of years. It likely resulted from rapid climate change as the supercontinent Gondwana moved over the South Pole, causing widespread glaciation that lowered sea levels by perhaps 100 meters, draining shallow seas that were diverse marine habitats. Glaciation cooled the planet, then rapid deglaciation and warming disrupted ecosystems further. Species adapted to stable, warm conditions couldn't survive the rapid swings. The late Devonian extinction, about 375 million years ago, eliminated about 75% of species over several million years in multiple pulses. The causes are debated, but may include asteroid impacts. Evidence for impact craters exists from this time, volcanic activity. The Vili traps in Siberia erupted during this period, and ocean anoxia, oxygen depletion in the oceans that killed marine life. The late Devonian was a time of major changes. Plants were colonizing land, creating soil and altering weathering patterns, possibly drawing down atmospheric CO2 and cooling the climate, which might have contributed to ocean circulation changes and anoxia. Reef-building organisms were particularly hard hit, and it took millions of years for reefs to recover. The Permian-Triassic extinction, about 252 million years ago, was the most severe, killing about 96% of marine species and 70% of terrestrial vertebrate species, making it the closest complex life has come to complete extinction. This great dying nearly ended complex life on Earth. The cause was likely massive volcanic eruptions in Siberia, the Siberian traps, which released enormous amounts of lava and gases over about 2 million years, though most erupted in pulses over several 100,000 years. The eruptions covered an area larger than Europe with lava up to 3 kilometers thick and released CO2, methane, and sulfur compounds that triggered global warming of perhaps 10 degrees C or more, ocean acidification, and oxygen depletion. Methane released from warming ocean sediments may have amplified warming. Hydrogen sulfide produced by bacteria in anoxic waters may have poisoned the oceans and atmosphere. The extinctions occurred in multiple phases, suggesting multiple mechanisms. Recovery took millions of years. The early Triassic was a depauperate time with low diversity and ecosystems dominated by a few opportunistic species. The Triassic-Jurassic extinction, about 201 million years ago, killed about 76% of species, possibly caused by volcanic eruptions associated with the breakup of the supercontinent Pangaea, which released carbon dioxide and warmed the planet. The Central Atlantic Magmatic Province, CAMP, one of the largest volcanic provinces on Earth, erupted during this time, spanning what is now eastern North America, Western Africa, South America, and southwestern Europe. The extinction paved the way for dinosaur dominance in the Jurassic and Cretaceous periods. Dinosaurs existed before the extinction, but were not dominant. After it, they became the dominant terrestrial vertebrates for 135 million years. The Cretaceous Paleogene, KPG extinction, about 66 million years ago, killed about 75% of species, including all non-avian dinosaurs. The cause was an asteroid impact. A 10-kilometer object struck the Yucatan Peninsula in Mexico, creating the Chicxulub crater, over 180 kilometers in diameter. The impact released energy equivalent to billions of nuclear weapons, about 100 teratons of TNT, triggering tsunamis hundreds of meters high that inundated coastlines. Global wildfires ignited by infrared radiation from material ejected into the upper atmosphere and falling back, and ejecting enough dust and aerosols into the atmosphere to block sunlight for months or years, causing a collapse of photosynthesis and global cooling. Sulfur dioxide from vaporized sulfate rocks in the target area created sulfuric acid aerosols that cooled the planet further and created acid rain. Photosynthesis-dependent ecosystems collapsed. Large animals, unable to find food and lacking adaptations to survive prolonged cold and dark, went extinct. Smaller animals, those that could burrow, hibernate, or survive on detritus and seeds, had better survival chances. These extinctions, while catastrophic, also created opportunities. Mass extinctions removed dominant groups and allowed other groups to diversify into vacated ecological niches. Mammals, which had been small and nocturnal during the Mesozoic, diversified explosively after dinosaurs went extinct, eventually giving rise to primates and humans. Birds, the surviving dinosaurs, also diversified. Each mass extinction reshuffled life, changing Earth's evolutionary trajectory. Currently, many scientists argue we're in the midst of a sixth mass extinction, this time caused not by asteroids or volcanoes, but by human activities, habitat destruction, climate change, pollution, overexploitation, and invasive species. Extinction rates are perhaps 101,000 times higher than background rates, and thousands of species are threatened with extinction. Whether this will develop into an event comparable to the Big Five depends largely on human actions over the coming centuries, particularly how we address climate change and habitat loss. Rocks record Earth's history through their formation, composition, and fossils. Rocks are classified into three main types based on how they form. Igneous rocks form from cooling magma or lava. Magma that cools slowly deep underground forms intrusive igneous rocks with large crystals visible to the naked eye, like granite, because slow cooling allows time for large crystals to grow. The Sierra Nevada mountains in California are a massive granite batholith, an intrusive igneous body exposed by millions of years of erosion removing overlying rock. Lava that cools quickly at the surface forms extrusive igneous rocks with tiny crystals or glassy texture, like basalt or obsidian, because rapid cooling doesn't allow time for large crystals. The Hawaiian Islands are composed primarily of basalt from volcanic eruptions. The composition of igneous rocks reflects the chemistry of the magma, which depends on the source. Melting oceanic crust produces basaltic magma rich in iron and magnesium, while melting continental crust produces more silica-rich granitic magma. Sedimentary rocks form from accumulated sediments, particles of rock, minerals, or biological material that are compacted and cemented over time. Sediments can originate from weathering and erosion of existing rocks, producing clastic sedimentary rocks like sandstone from sand-sized particles, shale from clay-sized particles, and conglomerate from gravel and cobbles. They can form from chemical precipitation, like rock salt or gypsum forming when bodies of water evaporate, concentrating dissolved minerals until they precipitate. Or they can be biological, like limestone forming from accumulated shells and coral skeletons, or coal forming from accumulated plant matter buried and compressed. Sedimentary rocks form in layers called beds or strata, with younger layers deposited on top of older layers, a principle called superposition. They often contain fossils, preserved remains or traces of ancient organisms, making them invaluable for understanding life's history. The Grand Canyon, carved by the Colorado River, exposes sedimentary layers spanning nearly 2 billion years, a remarkable record of changing environments from ancient oceans to rivers to deserts. Metamorphic rocks form when existing rocks are subjected to high temperature and pressure, typically deep in Earth's crust during mountain building or near intrusions of magma. The original rock's minerals recrystallize into new minerals stable under the new conditions, and the rock may develop new textures like the layered appearance of schist or gneiss, called foliation, where minerals are aligned by pressure. Metamorphic rocks can form from igneous, sedimentary, or other metamorphic rocks. For example, limestone metamorphoses into marble, sandstone into quartzite, shale into slate, then schist, then gneiss with increasing temperature and pressure. The sequence of metamorphic rocks provides a record of temperature and pressure conditions, helping geologists understand tectonic processes. The Himalayan mountains expose high-grade metamorphic rocks, showing the intense pressure and temperature conditions during continental collision. These three rock types cycle through the rock cycle. Igneous rocks weather into sediments that lithify into sedimentary rocks, which may be buried and metamorphosed, then partially melted to form new magma that solidifies into igneous rocks. The cycle has no fixed starting point or direction. Rocks can transform directly from any type into any other type depending on conditions. Over millions of years, rocks are continuously recycled. Subduction returns surface rocks into the mantle where they melt or contribute to mantle composition. Uplift and erosion expose deep rocks at the surface where weathering begins breaking them down. Deposition in ocean basins buries sediments, beginning their transformation into sedimentary rock. Mountain building metamorphoses and deforms rocks. The rock cycle is driven by plate tectonics and powered ultimately by Earth's internal heat. Dating rocks reveals Earth's history. Relative dating, determining whether one rock is older or younger than another, uses principles like superposition. In undisturbed sequences, older rocks are below younger rocks, Cross-cutting relationships features that cut across rocks are younger than the rocks they cut. If a dike intrudes into surrounding rock, the dike is younger, and fossil succession, fossils appear in a specific order through geological time, with older fossils below younger ones, because evolution is directional. These principles allow ordering events and constructing geological histories, even without absolute ages. Absolute dating, determining a rock's age in years, primarily uses radiometric dating. Certain elements naturally decay radioactively at constant rates, transforming into different elements. For example, uranium-238 decays through a series of steps into lead-206, potassium-40 decays into argon-40, and rubidium-87 decays into strontium-87. By measuring the ratio of parent to daughter isotopes and knowing the decay rate, half-life, geologists can calculate how long decay has been occurring, the rock's age. This works because radioactive decay is a nuclear process unaffected by external conditions like temperature or pressure, so decay rates are constant and reliable. Different isotope systems are useful for different age ranges and rock types. Carbon-14, with a half-life of 5,730 years, is useful for dating organic materials up to about 50,000 years old, beyond which too little carbon-14 remains for accurate measurement. Carbon-14 is produced in the atmosphere by cosmic rays and incorporated into living organisms. When an organism dies, carbon-14 intake stops and the isotope decays, allowing age determination. Potassium-40, decaying to argon-40 with a half-life of 1.25 billion years, can date rocks billions of years old. It's particularly useful for volcanic rocks where argon gas escapes during eruption, resetting the clock, then accumulates as potassium decays after the rock solidifies. Uranium, with a half-life of 4.5 billion years, has been used to date the oldest rocks on Earth and meteorites, providing Earth's age of 4.54 billion years. The oldest intact rocks on Earth are about 4.03 billion years old, the Acasta gneiss found in northwestern Canada. Older rocks must exist or have existed, but plate tectonics recycles crust, and erosion destroys rocks, removing most of the early geological record. The first 500 million years of Earth's history, the Hadean Eon, has virtually no rock record because the surface was largely molten or continuously reworked by impacts and volcanism. However, mineral grains survive longer than the rocks containing them. The oldest known materials on Earth are tiny zircon crystals from Jack Hills in Western Australia, dated to 4.4 billion years old, nearly as old as Earth itself. These zircons crystallized in magma just tens of millions of years after Earth formed. Amazingly, oxygen isotope ratios in the zircons suggest the magma interacted with liquid water, implying oceans existed by 4.4 billion years ago, much earlier than previously thought. These ancient zircons preserve a tiny glimpse of the Hadean, Earth's earliest, most poorly known period, suggesting conditions may have been less hellish than the name implies. We've traveled through deep time tonight. From Earth's violent birth in the swirling debris of the solar nebula, built piece by piece through countless collisions over millions of years, to the moon-forming impact that nearly destroyed the young planet, but left behind a companion that has stabilized our world's climate ever since. From the layered interior, where solid iron inner core spins within liquid iron outer core, generating the magnetic field shielding us from solar wind, through the flowing mantle driving plates across the surface at centimeters per year, to the thin crust we walk upon, constantly reshaped by forces operating on timescales far beyond human perception. We've traced water's journey from space to ocean, atmosphere to land and back again, cycling endlessly through evaporation, precipitation, and flow, spending days in the atmosphere, weeks in rivers, millennia in glaciers and deep ocean. We've seen how uneven solar heating drives winds and ocean currents transporting heat from equator to poles, moderating temperatures and making much of Earth habitable. We've descended through atmosphere layers from weather-creating troposphere, where temperature decreases with altitude, to ozone-containing stratosphere, where ultraviolet absorption warms the air and protects life below, to mesosphere, where meteors burn, to thermosphere, where auroras dance, to exosphere gradually fading into space. We've watched plates drift centimeters per year for millions of years, opening oceans like the Atlantic, closing ancient seas like Tethys, colliding continents to raise mountains like the Himalayas that continue rising today, though erosion simultaneously wears them down grain by grain. We've witnessed earthquakes releasing stress accumulated over decades in seconds of violent shaking, waves radiating through the planet, revealing its internal structure. We've seen volcanoes bringing molten rock from depths of hundreds of kilometers to the surface, building mountains, releasing gases that maintain the atmosphere and oceans, occasionally erupting with enough force to affect global climate for years. We've experienced ice ages when ice sheets, kilometers thick, covered continents, lowering sea levels over 100 meters, transforming geography and climate, exposing land bridges that allowed species, including humans, to migrate between continents. We've seen ice retreat within a few thousand years as orbital parameters shifted, melting ice raising seas, drowning coastlines, establishing the climate that has persisted for 11,700 years, allowing agriculture and civilization to develop. We've glimpsed life's emergence at least 3.5 billion years ago in a world with no free oxygen, its transformation of the atmosphere through photosynthesis, its survival through 5 mass extinctions, its endless adaptation to changing conditions, diversifying into millions of species, filling every available niche from deep-sea vents to high mountains, from polar ice to tropical forests, from acidic hot springs to the driest deserts. But here's the essential truth: you're part of all this. Earth isn't just a planet you live on, you're made of Earth. Every atom in your body was once part of this planet's rocks, water, or atmosphere. The calcium in your bones came from rocks dissolved by weathering, carried by rivers to the ocean where marine organisms extracted it to build shells, recycled through the food chain when you consumed plants or animals. The oxygen you breathe was produced by photosynthetic organisms, as has been true for billions of years, each breath connecting you to cyanobacteria that transformed the atmosphere 2.4 billion years ago, and to plants that continue producing oxygen today. The water in your cells cycled through oceans, atmosphere, glaciers, rivers, other organisms countless times over Earth's history. You're a temporary arrangement of Earth's atoms, aware and awake for a brief moment in geological time, a pattern of organization that emerged from 4 billion years of evolution, maintaining yourself against entropy through constant exchange of matter and energy with the environment, destined to return your borrowed atoms to the planet when you die, completing a cycle that has repeated for every organism that ever lived. You're also living in a unique moment in Earth's history. For the first time, a single species, humans, has become a geological force, altering the planet at global scales faster than many natural processes. We've changed atmospheric composition, raising CO2 to levels not seen in millions of years, from 280 parts per million before industrialization to over 420 ppm today, warming the planet about 1 degrees C and committing to further warming. We've transformed half of Earth's land surface through agriculture, cities, infrastructure, and resource extraction, altering ecosystems and disrupting nutrient cycles. We've changed the climate, causing warming that will reshape coastlines as ice melts and seas rise, alter weather patterns with more intense droughts, floods, and storms, and shift species ranges poleward and upward as they track changing temperatures. We've driven species extinctions at rates perhaps 1,000 times natural background rates, eliminating species before they've been described and named, disrupting ecosystems and reducing biodiversity that took hundreds of millions of years to accumulate. We've created new materials like plastics that will persist in the geological record for millions of years, potentially serving as a marker of the Anthropocene in future rock layers. We've left radioactive isotopes from nuclear weapons testing globally distributed in sediments. We've moved species around the world, creating novel ecosystems. We've altered the nitrogen cycle through fertilizer production, the phosphorus cycle through mining, and the carbon cycle through fossil fuel burning and deforestation. Geologists debate whether we've entered a new epoch, the Anthropocene, the age of humans, though the International Commission on Stratigraphy has not yet officially recognized it. Regardless of nomenclature, Earth's trajectory has changed. Climate models project warming of 2-4 degrees C or more by 2100 depending on emissions, with corresponding sea level rise, ecosystem disruptions, and challenges to human societies. The last time CO2 was this high, about 3 million years ago in the Pliocene, global temperatures were 2-3 degrees C warmer, sea level was 1525 meters higher, and the Arctic had forests instead of ice. We're driving the planet toward conditions not seen since long before humans existed, doing in centuries what usually takes millennia, too fast for many species to adapt through evolution. This is sobering but also empowering. We've caused these changes, and we have the capacity to limit them. Understanding Earth, its systems, its history, its sensitivities, provides the knowledge needed to make informed decisions about how we interact with the planet. Earth's climate system has changed dramatically in the past, sometimes gradually over millions of years, sometimes catastrophically in geological eye blinks. These changes teach us that climate can shift rapidly once tipping points are crossed, that feedbacks can amplify small changes into large ones through positive feedback loops, that Earth's life has proven remarkably resilient over billions of years, surviving catastrophes that would seem apocalyptic, but individual species haven't, including most species that ever existed now extinct, and that the planet will continue regardless of what we do, but the world we leave for future generations depends entirely on choices made now. Earth is 4.54 billion years old. Modern humans have existed for about 300,000 years, 0.007% of Earth's history, barely perceptible on a timeline spanning from formation to present. Recorded history spans perhaps 5,000 years, 0.0001% of Earth's age, a tiny fraction of the story. Yet in just the past 200 years, a mere 0.000004% of Earth's history, we've altered the planet's trajectory, changing atmospheric composition faster than almost any natural event except large asteroid impacts and massive volcanic eruptions, warming the climate, raising seas, and driving species extinct. We're unlikely to destroy Earth. It has survived asteroid impacts that vaporized oceans, volcanic supereruptions that covered continents in lava, snowball freezing that covered the planet in ice, hothouse warming with no polar ice caps, and will outlast humanity by billions of years, eventually being consumed when the sun becomes a red giant in about 5 billion years. But Earth itself will persist, until then barring some cosmic catastrophe. But we can and are changing the planet's habitability for ourselves and countless other species. The geological record teaches that such changes have consequences, that systems pushed far from equilibrium can respond abruptly and unpredictably with tipping points that cause rapid transitions, that recovery from major disruptions takes millions of years through evolution, generating new species to replace those lost, far longer than civilizations persist. Earth doesn't care whether humans thrive or struggle. The planet will continue its ancient processes regardless, indifferent to our presence or absence. But we should care. This is the only home we've ever known, the only world we can reach with current technology, the planet that provided everything needed for life, including our own evolution and sustenance. If you're still awake, there are more videos waiting. But if sleep found you somewhere along the way, then this worked exactly as it should. Rest well, knowing that beneath you, around you, the planet continues its ancient processes that operated billions of years before humans existed and will continue billions of years after we're gone. The inner core spins, gaining a quarter turn each century relative to the surface. The outer core churns, generating magnetic field lines that wander through space, occasionally reversing polarity. The mantle flows at centimeters per year, carrying plates across the surface, opening oceans, closing seas, raising mountains. Magma rises where plates diverge, creating new crust at mid-ocean ridges. Old crust descends at subduction zones, recycling back into the mantle. Mountains rise imperceptibly, millimeters per year sustained over millions of years, erode grain by grain carried by rivers to the sea. Oceans cycle heat from equator to poles. Atmosphere churns, winds flowing in cells, storms forming and dissipating. Water evaporates from oceans, precipitates on land, flows in rivers, infiltrates groundwater, returns to the sea. Life metabolizes, breathes, grows, reproduces, dies, is decomposed by bacteria and fungi, returns to soil and sea, nutrients recycled to support new life. These processes operated billions of years before humans existed and will continue billions of years after we're gone. We're passengers on this planet for a brief moment, privileged to be aware, to understand through science what we're part of, to have discovered our place in deep time and vast space, to know that we live on a spinning sphere of layered rock and metal with paper-thin ocean and atmosphere, orbiting an ordinary star in an ordinary galaxy in a universe containing hundreds of billions of galaxies, each with hundreds of billions of stars and probably countless planets. Yet among all those worlds, Earth is unique to us, the only one confirmed to harbor life, the only one we can reach, the only home we've ever known. Earth has provided everything needed for life, including our own. It continues spinning through space, 365.25 days per year, every year for 4.54 billion years and counting. A blue sphere dotted with green and brown continents, wrapped in white clouds, glowing in reflected sunlight, carrying all of us through the cosmos at 30 kilometers per second in orbit around the sun, while the sun itself moves at 220 kilometers per second around the Milky Way galaxy. While the galaxy moves through space toward the constellation Hydra at 600 kilometers per second. You're traveling through the universe at hundreds of kilometers per second right now, though you feel perfectly still, standing on a spinning planet that feels solid and stable though it's mostly molten inside, breathing an atmosphere that's 78% nitrogen but feeling nothing, looking at a sky that appears blue though it's transparent, experiencing a present moment that's already passed by the time you perceive it, made of atoms forged in stars that exploded billions of years ago. Living on a planet that's just the right distance from its star, just the right size, with just the right atmosphere, just the right amount of water, just the right magnetic field, just the right moon, just the right conditions to support the particular form of carbon-based life that emerged and evolved and eventually became conscious and built civilizations and developed science to understand where we came from and what we're part of. See you next time.
you.